Something extraordinary happened 48 hours ago that has fundamentally changed our understanding of 3I Atlas's trajectory and ultimate destination. China's Tianwen-1 Mars orbiter, which has been conducting scientific operations around the Red Planet since February 2021, was repositioned on November 15th to conduct precision tracking observations of 3I Atlas using its high-resolution cameras and advanced navigation systems. The data that Tianwen-1 transmitted back to Earth, which was shared with the international astronomical community yesterday through the International Astronomical Union's Central Bureau for Astronomical Telegrams, provides trajectory measurements with a precision approximately 10 times better than anything we've achieved using ground-based telescopes. And what those measurements reveal is both fascinating and deeply concerning. Let me start by explaining why spacecraft-based observations provide such superior accuracy compared to ground-based tracking. When we observe objects from Earth, we're looking through our atmosphere, hundreds of kilometers of turbulent air that distorts and blurs images. Even with adaptive optics systems that partially correct for atmospheric distortion, we're fundamentally limited in the precision we can achieve for position measurements. Additionally, ground-based observers are confined to viewing from one location in space, Earth's surface, which limits our ability to measure three-dimensional positions and velocities with high accuracy. Spacecraft observing from space don't face these limitations. There's no atmosphere to distort images. The spacecraft's position is precisely known through radio tracking and orbital dynamics. And critically, a spacecraft at Mars provides a different viewpoint, a baseline of approximately 200 million kilometers from Earth, which enables parallax measurements that dramatically improve distance and velocity determinations. This is the same principle as how your two eyes, separated by just a few centimeters, give you depth perception through parallax. Tianwen-1 at Mars and telescopes on Earth provide eyes separated by an astronomical distance, enabling extraordinarily precise three-dimensional position measurements. Dr. Li Wei at the China National Space Administration, speaking at a hastily organized press conference in Beijing yesterday, explained the observation campaign.
Tianwen-1 has completed its primary mission objectives for Mars science and has operational capability to support other scientific priorities, he stated. When the international community expressed interest in obtaining higher precision trajectory measurements for 3I Atlas, we recognized that Tianwen-1 was uniquely positioned to contribute. Between November 15th and November 17th, we conducted 12 separate observation sessions using Tianwen-1's high-resolution imaging camera, acquiring position measurements with timing precision of milliseconds and spatial resolution approaching 100 meters at 318 light-years distance. That precision is remarkable. To put it in perspective, previous ground-based measurements had uncertainties of roughly 1,000 to 2,000 kilometers in 3I Atlas's position. Tianwen-1's measurements reduced that uncertainty to approximately 100 to 150 kilometers, an order of magnitude improvement. For velocity measurements, the improvement is even more dramatic. Ground-based Doppler spectroscopy could measure velocity to precision of about 1/10 of a kilometer per second. Tianwen-1's parallax measurements, combined with precise timing, provide velocity precision of approximately 0.01 kilometers per second, 10 times better. Why does this level of precision matter? Because trajectory prediction accuracy scales with measurement precision. Small errors in position and velocity measurements propagate forward into time as you calculate future positions, and those errors grow larger the further into the future you project. With ground-based measurements, our predictions for where 3I Atlas would be in December had uncertainties of tens of thousands of kilometers. That's large enough that we couldn't definitively determine whether certain close approach scenarios were possible or ruled out. Tianwen-1's data reduces those uncertainties by an order of magnitude, which means we can now predict the trajectory with far greater confidence and much further into the future. So what does the improved trajectory reveal? Dr. Zhong Ming at the Chinese Academy of Sciences led the trajectory analysis using Tianwen-1's data. The findings published in a rapid release paper on the RxI preprint server yesterday are striking. The refined trajectory shows that 3I Atlas will pass significantly closer to Earth than previous estimates predicted.
Dr. Zhang reported, "Our calculations, with error bars 10 times smaller than previous work, indicate closest approach will occur on December 24th at 1837 hours UTC, at a distance of 0.087 astronomical units, approximately 1.3 million kilometers from Earth's center. This is roughly 3.4 times the distance from Earth to the Moon. Compared to previous estimates of 0.02 AU, or about 3 million kilometers, the object will be more than twice as close as we thought." Let me emphasize what this means. Previous trajectory estimates had 3I Atlas passing Earth at about 7.8 lunar distances. The new trajectory shows closest approach at only 3.4 lunar distances. That's not a trivial difference. At 1.3 million kilometers, 3I Atlas will be well within Earth's gravitational sphere of influence, the region where Earth gravity dominates over the Sun's. Any small objects released from 3I Atlas at that distance could easily be captured into Earth orbit, or, with minimal velocity changes, be placed on trajectories that intersect Earth's atmosphere. But the distance isn't the most concerning aspect of the new trajectory. Dr. Zhang's analysis reveals something even more significant. The approach geometry has changed. Previous calculations suggested 3I Atlas would approach from a direction roughly 40 degrees above Earth's orbital plane, pass through the plane at closest approach, and continue on a hyperbolic trajectory that would take it back out of the solar system at a steep angle. The refined trajectory tells a different story. The approach is much more aligned with Earth's orbital plane than we previously calculated, Dr. Zhang explained. 3I Atlas will approach at an angle of approximately 12 degrees to the ecliptic plane rather than 40 degrees. This means the relative velocity at closest approach is lower, approximately 41 kilometers per second relative to Earth, instead of the 54 kilometers per second we calculated using ground-based data. Lower relative velocity is significant for two reasons. First, it makes gravitational capture more efficient if objects are released at close approach. And second, it means 3I Atlas experiences a stronger gravitational deflection from Earth's gravity. Well, that gravitational deflection is where the trajectory gets really interesting and really concerning. When objects pass close to planets, the planet's gravity bends their trajectory, a phenomenon called a gravitational slingshot or gravity assist. The amount of deflection depends on how close the object passes and how fast it's moving. Closer passes and slower speeds produce stronger deflection. With the refined trajectory showing a closer approach and slower relative velocity than previously thought, the gravitational deflection effect is much more pronounced. Dr. Zhang's calculations show that Earth's gravity will deflect 3I Atlas's trajectory by approximately 17 degrees, a substantial bend in its path. But here's the critical finding. The direction of that deflection is not random. The geometry is such that Earth's gravity will bend 3I Atlas's outbound trajectory toward the inner solar system, rather than flinging it outward after the Earth encounter. 3I Atlas's trajectory will take it closer to the Sun, not farther away. Dr. Zhang stated, the perihelion distance, closest approach to the Sun, will be approximately 0.31 AU, which is well inside the orbit of Mercury. The object will reach perihelion on February 8, 2026, approximately 6 weeks after the Earth encounter. The thermal stress of passing that close to the Sun, combined with the radiation environment inside Mercury's orbit, will produce dramatic effects on the object's structure and composition. This trajectory revision has enormous implications that ripple across multiple aspects of how we understand 3I Atlas and what we should expect in the coming weeks. Let me work through these implications systematically. Implication 1. Enhanced observation opportunities. A closer approach means we'll be able to observe 3I Atlas in far greater detail than previously anticipated. At 1.3 million kilometers, the object will be close enough that even modest amateur telescopes will be able to see it as a non-stellar object, a small disk, rather than a point of light. Professional observatories will achieve resolution approaching 10 meters per pixel in the best images, which means we'll be able to see surface features the size of large buildings, if such features exist. Dr. Amanda Peterson at the University of Hawaii, who specializes in small body observations, commented on the observational implications. This is an extraordinary opportunity. We'll be able to conduct observations during the close approach that would normally require sending a spacecraft. Spectroscopy will reveal composition in unprecedented detail.
Radar observations will penetrate deep into the interior and reveal three-dimensional structure. Thermal imaging will map temperature variations across the entire surface. If there's anything unusual about this object, artificial structures, geometric features, evidence of processing or manufacturing, we'll see it during the close approach window. The observation campaign is already being coordinated. NASA, ESA, the Chinese National Space Administration, the Russian Space Agency, Roscosmos, and space agencies from Japan, India, and other nations are all committing resources. The international coordination is remarkable. Every major telescope on Earth will be observing 3I Atlas continuously during the 48-hour window around closest approach. We'll gather more data about this object in 2 days than we gathered about Oumuamua during its entire passage through the solar system. Implication 2. Increased close approach risks. While still passing at a safe distance by absolute standards, the closer approach increases the probability of secondary effects that could pose risks. The most obvious is debris. If 3I Atlas sheds fragments, either through natural outgassing or through deliberate deployment. If it's artificial, those fragments will be on trajectories very similar to the main object. Some fragments could have slightly different velocities that place them on Earth-intersecting paths. Dr. Robert Chen at MIT calculated the debris risk scenarios. If 3I Atlas releases a fragment with a velocity change of just 50 meters per second relative to the main body at closest approach, that fragment could impact Earth's atmosphere within days to weeks, he reported. That's a very small velocity change, comparable to a gentle push. Natural outgassing can easily produce such velocity changes, so even if the main object passes safely, we face a heightened risk of fragment impacts for several weeks after the encounter. The risk isn't catastrophic. We're not talking about extension-level impact. Most fragments would be small, likely burning up as meteors in the upper atmosphere. But larger pieces, anything more than a few meters in size, could reach the surface and cause regional damage. The uncertainty about 3I Atlas's composition makes damage assessment difficult. If it's primarily ice, fragments would ablate completely in the atmosphere. If it has rocky or metallic components, surface impacts become more likely. NASA's Planetary Defense Coordination Office has been activated to monitor for fragments. Dr. Lindley Johnson, who heads the office, issued a statement yesterday. We're treating the 3I Atlas close approach as a potential impact threat scenario for planning purposes. That doesn't mean we expect impact. The probabilities remain low, but the closer approach and fragment uncertainty justify elevated monitoring and preparedness. We're coordinating with civil defense agencies to ensure emergency response capabilities are ready if needed. Implication 3. Gravitational effects on Earth. At 1.3 million kilometers, 3I Atlas is close enough that its gravity will have measurable, though very small, effects on Earth. The tidal force from an object depends on its mass and distance. With 3I Atlas's estimated mass of 33 billion tons and the revised close approach distance, the tidal force will be approximately 1/billionth of the tidal force from the Moon. That sounds negligible, and for most practical purposes it is. You won't feel it, it won't affect ocean tides noticeably, it won't trigger earthquakes, but it is measurable with sensitive instruments. Dr. Sarah Williams at the European Space Agency explained the significance. We'll use gravimeters, instruments that measure tiny variations in Earth's gravitational field, to detect the gravitational pull from 3I Atlas during closest approach. Those measurements will allow us to independently determine 3I Atlas's mass with much higher precision than we can achieve through other methods. That mass determination will tell us definitively whether the object is solid, porous, or hollow, which bears directly on the question of whether it's natural or artificial. If the measured mass matches what we expect for a solid or rubble pile object with natural composition, that supports natural origin. If the measured mass is significantly lower, suggesting hollow interior or very low density construction, that would support artificial origin. This is a crucial test that we couldn't perform at greater distances. Implication 4. The post-solar trajectory. Perhaps the most significant implication of Tianwen-1's trajectory refinement is what happens after the Earth encounter. The deflection toward a much closer solar approach raises fascinating possibilities and troubling questions. If 3I Atlas is a natural comet, passing 0.31 AU from the Sun, closer than Mercury, will produce extreme heating and outgassing. The solar intensity at that distance is approximately 10 times higher than at Earth's orbit. Ices that are stable farther out will sublimate explosively. The object will likely develop an enormous tail, possibly visible to the naked eye from Earth. Even at that distance, we might see the object fragment under thermal stress. This would be a spectacular astronomical event, a once-in-a-lifetime observation of an interstellar comet passing through intense solar heating. But if 3I Atlas is artificial, the close solar approach takes on different meaning. Dr. Jennifer Hammond at Oxford examined this scenario. If this is a spacecraft or probe, a close solar path could serve several purposes, she explained. 1. It could be a gravity assist maneuver, using the Sun's gravity to change trajectory for some other destination. 2. It could be using close solar approach for power generation, harvesting solar energy to recharge systems. 3. It could be a disposal trajectory, deliberately flying into intense solar heating to destroy the craft after its mission is complete. Each interpretation has different implications for what we should expect to observe. The post-solar trajectory is equally interesting. Dr. Zhang's calculations show that after passing the Sun, 3I Atlas's trajectory will take it back outward, but on a different path than it entered. The combined gravitational effects of Earth and Sun encounters will send the object on a trajectory that exits the solar system in a different direction than it entered. Dr. Zhang explained the outbound trajectory will take it toward the constellation Lyra rather than back toward its origin direction. Whether this is natural gravitational dynamics or indicates deliberate navigation, we cannot yet determine. Implication 5. Communication window enhancement. The closer approach significantly enhances our ability to communicate with 3I Atlas. If it's artificial and has radio receivers, radio signals weaken with distance. According to the inverse square law, doubling the distance quarters the signal strength. Halving the distance quadruples the signal strength. At the revised close approach distance of 1.3 million kilometers versus the previous estimate of 3 million kilometers, transmitted signals from Earth will be approximately 5.3 times stronger at 3I Atlas than we previously calculated. That's a substantial improvement in communication capability. Dr. Jennifer Williams at the SETI Institute is coordinating an enhanced communication campaign. We're planning intensive transmission efforts during the close approach window, she explained. We'll use multiple transmitters, broadcasting across a range of frequencies with message content designed to maximize the probability of detection and comprehension.
We're including mathematical concepts, physical constants, information about Earth and humanity, and explicit invitations for response. If there's any receiver aboard 3 Atlas capable of detecting our signals, the close approach window is our best opportunity to make contact. The transmission schedule includes continuous broadcast starting December 22nd, intensifying during closest approach on December 24th, and continuing through December 26th. The message content will be broadcast in multiple languages, not human languages, but mathematical and scientific languages that any technological civilization should understand. Prime numbers, the periodic table, fundamental physical constants, pictorial representations of the solar system and Earth, all encoded in formats designed for maximum clarity. Will they respond? We don't know. If 3 Atlas is natural, obviously there will be no response. If it's artificial but not designed to communicate with civilizations it encounters, there might still be no response. But if communication is part of its mission, the close approach provides optimal conditions for making that communication happen. Implication 6. Mission planning for follow-up. The refined trajectory has implications for any spacecraft missions attempting to study 3I Atlas. With the object passing closer to Earth, the velocity change required for a spacecraft to match velocities and achieve rendezvous is actually lower than previously calculated. That makes certain mission profiles more feasible. Dr. Amanda Foster at MIT has been working on mission concepts with the revised trajectory. A fast flyby mission launched from Earth around the time of 3-1 Atlas's close approach could intercept the object shortly before solar perihelion. She explained that would provide spectacular observations during the most thermally active phase of the encounter. Alternatively, a mission could target the outbound leg, intercepting after perihelion to study the effects of extreme solar heating. Several space agencies are actively evaluating rapid response missions. The European Space Agency's proposed flyby mission is now being reconsidered with trajectory designs optimized for the revised path. China has announced they're evaluating whether to repurpose an existing spacecraft, possibly one of their lunar program craft, for a 3-1 Atlas flyby. Even NASA, which had previously concluded mission options were impractical given budget and timeline, is reassessing whether repurposing an existing mission might be feasible. The challenge remains timeline. Any spacecraft would need to launch within the next few weeks to intercept 3I Atlas before it leaves the intersolar system. That requires extraordinary speed in decision-making and spacecraft preparation, speed that governmental bureaucracies don't typically achieve. But the refined trajectory has renewed interest and urgency, which might overcome bureaucratic inertia. Implication 7. Public safety and preparedness. The closer approach distance, while still very safe by astronomical standards, has triggered public safety considerations by governmental authorities. Several national emergency management agencies have issued advisories, not because of any specific danger, but as prudent preparedness given uncertainties. The advisories generally recommend that people stay informed through official channels during the December 22 to 26 window, that they know their local emergency procedures, and that they have basic emergency supplies available. The tone is explicitly non-alarmist, emphasizing that there's no expected danger, but that preparedness is wise when dealing with unprecedented situations. Unfortunately, despite careful official communication, some panic has emerged in vulnerable populations. There have been runs on emergency supplies in some regions. We're including mathematical concepts, physical constants, information about Earth and humanity, and explicit invitations for response. If there's any receiver aboard 3 Atlas capable of detecting our signals, the close approach window is our best opportunity to make contact. The transmission schedule includes continuous broadcast starting December 22nd, intensifying during closest approach on December 24th, and continuing through December 26th. The message content will be broadcast in multiple languages, not human languages, but mathematical and scientific languages that any technological civilization should understand. Prime numbers, the periodic table, fundamental physical constants, pictorial representations of the solar system and Earth, all encoded in formats designed for maximum clarity. Will they respond? We don't know. If 3 Atlas is natural, obviously there will be no response. If it's artificial but not designed to communicate with civilizations it encounters, there might still be no response. But if communication is part of its mission, the close approach provides optimal conditions for making that communication happen. Implication 6. Mission planning for follow-up. The refined trajectory has implications for any spacecraft missions attempting to study 3I Atlas. With the object passing closer to Earth, the velocity change required for a spacecraft to match velocities and achieve rendezvous is actually lower than previously calculated. That makes certain mission profiles more feasible. Dr. Amanda Foster at MIT has been working on mission concepts with the revised trajectory. A fast flyby mission launched from Earth around the time of 3-1 Atlas's close approach could intercept the object shortly before solar perihelion. She explained that would provide spectacular observations during the most thermally active phase of the encounter. Alternatively, a mission could target the outbound leg, intercepting after perihelion to study the effects of extreme solar heating. Several space agencies are actively evaluating rapid response missions. The European Space Agency's proposed flyby mission is now being reconsidered with trajectory designs optimized for the revised path. China has announced they're evaluating whether to repurpose an existing spacecraft, possibly one of their lunar program craft, for a 3-1 Atlas flyby. Even NASA, which had previously concluded mission options were impractical given budget and timeline, is reassessing whether repurposing an existing mission might be feasible. The challenge remains timeline. Any spacecraft would need to launch within the next few weeks to intercept 3I Atlas before it leaves the intersolar system. That requires extraordinary speed in decision-making and spacecraft preparation, speed that governmental bureaucracies don't typically achieve. But the refined trajectory has renewed interest and urgency, which might overcome bureaucratic inertia. Implication 7. Public safety and preparedness. The closer approach distance, while still very safe by astronomical standards, has triggered public safety considerations by governmental authorities. Several national emergency management agencies have issued advisories, not because of any specific danger, but as prudent preparedness given uncertainties. The advisories generally recommend that people stay informed through official channels during the December 22 to 26 window, that they know their local emergency procedures, and that they have basic emergency supplies available. The tone is explicitly non-alarmist, emphasizing that there's no expected danger, but that preparedness is wise when dealing with unprecedented situations. Unfortunately, despite careful official communication, some panic has emerged in vulnerable populations. There have been runs on emergency supplies in some regions,